Okay.
Alright, so this is CPU 233. We created a CPU VHDL, and then for our final project we created something that ran on it in assembly. And I created an interpretation of John Conway's Game of Life, which is a cellular automa, which means that basically you have a grid of 30 by 40 cells on the screen. And the cells can either be alive or dead. If they're alive, they're green. And every turn, whether or not the cell will be alive or dead next turn is dependent on how many live neighbors it has in the current turn. So we can adjust the speed through the switches here, and you'll see that these are pretty stable patterns that's up right now, and we'll just keep doing the same thing over and over again. We can also introduce some just kind of random input to see what it does. And I'll show you some of the patterns that will emerge. You notice it just kind of looks like cell life or bacteria growth or something. That's why it's called a game of life. So you just get some cool patterns that eventually you'll see shapes like these, or the blocks that are stable patterns that will just stay. And then you'll get oscillators that will just have like two different states they go back and forth in. And I also put in a function in the game where you can add stuff. So you'll see right there I added that line, and that's just a basic oscillator, just goes back and forth. And I spent a lot of time while I was compiling just staring at it. So yeah, that's basically the game. You can also hit the C key and it clears it.
Tell us about what you did with the video RAM.
So with the video RAM, it was originally supposed to be mostly use output to the VRAM, and then that was written to the screen. But I also use the video RAM as memory for holding the current state of the board. So like, for example, if I pause it, right now the video memory is these pixel locations are written to green. So to determine the next state of the board, the CPU reads that in, figures out how many neighbors each cell has, and then makes it alive or dead depending on how many neighbors it has. And we have another module that we're using as memory that is similar to the VRAM, but it isn't actually being written to the screen. It's just another copy that we use to create the next state of the game. And once that's completely created, then we write that to the VRAM, and that puts the next state up.
Very good. Thank you.